All right. Thank you, everyone, for joining this month's Kitchener-Waterloo Video Tech Meetup. I'm joined by two speakers from IMAX. Hojat Yeganeh, he's the senior manager at IMAX Labs, and he's going to discuss how he and his team developed the film grain similarity objective metric, which measures film grain fidelity. And then after Hojat's talk, we have Major Jang, PhD research scientist at IMAX Labs, and he's going to discuss how his team developed a large multimodal model, LMM, framework for per title video encoding optimization. So take it away, Hojat.
Thank you, Chris, for the introduction. Let me share my window. Okay. Okay. I hope everyone sees this. Okay, so once again, thank you, Chris, for giving us this opportunity to talk about our recent observation findings or novel works and share it with the community. In my talk, I will be talking about one of the recent accomplishment that we have made inside our IMAX CT labs, and that is designing the very first version of the film grain similarity metric. I think this is one of the kind, and no one has it so far. But it was a very, very challenging task for sure. I start with the statement. Okay, what was the problem that we are trying to solve? So, what was the problem or the main motivator behind designing this objective metric or objective model to measure the fidelity in film grains? So in the left-hand side, this is the source, and the right-hand side is what the industry today does it today and then delivers it today to your homes. And in fact, if you pay more attention to the grain, like specifically on the train, also in the sky, you would agree with me. I'm not sure how it goes through the Google Meet though, but if I stop here at this frame and then you compare the texture, the film grain texture on the left hand side and the right hand side, you agree that okay, there's a huge difference, there's a problem. So even by spending 10 megabits per second for an SDR UHD frame, and the frame is pretty much a static frame. You don't see a lot of action. It's not very complex. It's kind of a static frame, but like and with moving grain or so. But even for this frame, you see that how the encoders struggle with this kind of high entropy texture or signal, which is called film grain. So you may ask, what is special about film grain? Okay, who cares about film grain? Let's just spend 10 megabits per second. It's very high. Not many companies today spend 10 megabits per second for SDR UHD. But you may ask, what's the big deal with the film grain? Okay, why I'm caring about film grain? So the thing is that film grain matters for film makers, for directors, for content creators. Film grain helps them to bring a nostalgia, let's say, to audiences. It helps them to start or set up a mood and atmosphere for the content. It helps them to introduce a different kind of cinematic authenticity. So, or it's part of the creative intent. So, film grain matters a lot to filmmakers and the directors. And it's come from the very, very old era when they started shooting films and movies in analog film. And for somehow, it turns out the human visual system likes those kind of film grain or the native film grain that happens because of the light exposure on film. So again, film grain is a very, very essential part of the storytelling and filmmakers and like content creators. But of course, it's not the compression friendly, right? So the compression algorithm coders, they hate dealing with film grain or very high entropy signal like film grain. So what's a typical solution today that like people or the streamers use today to handle or to deliver content with film grain? It's a very simple solution, just increase the bitrate values. The only option that they have today in the typical scenarios and frameworks is to increase the bitrate values. But the question is that, okay, I know this is a very feasible approach. It may work. So for example, here you see that by spending 35 megabit per second, the film grain on the right-hand side looks pretty much the same on the left-hand side, even though you still miss some film grain in the sky, but somehow it works, like spending more bits on the content. But 35 megabits per second is huge for the streamers. And at the same time, the main question is that why 35 megabit per second? Why not 20? Why not 40? Is 35 megabit per second enough or not? So it requires a lot of subjective effort. So they need to watch content multiple times on TVs and then decide whether 25 is enough, 10 is enough, 15 is enough, 35 is enough. At the same time, scene by scene, film grain changes. Like this film grain is different for scene by scene, and it's a very, very cumbersome. It's not a practical to watch every scene and adjust and tune the bitrate values when encoding that special scene. So that means that we need somehow to automate this, even if we wanted to increase the bitrate value. So we need a metric for that. It's a metric that can measure the film grain similarity between the source and the encoded content or encoded stream. So what is the alternative today in the industry? The alternative is film grain synthesis. It's an elegant idea. It was proposed like a decade ago, or less than a decade ago, but it still is not widely adopted because of backward compatibility, because of some of the issues that we have in the frameworks, the adoption of the new codecs. But this is an elegant idea. So film grain synthesis helps us to save a lot of bits on content with film grain. How it works? So at the beginning, so they remove film grain from the source side, and then they, by just applying a denoiser or degrainer or so, and then they come up with some sort of a grain estimation. They come up with a statistical model for that particular grain after removing the grain, and then the clean content goes to encoder. Okay, encoder, they love clean content without having a lot of entropy. So they can easily encode that content, that clean content without film grain, using, let's say, a pretty much lower bandwidth or bitrate values. And at the decoder side, we can add those grains back or in the display side. So after injecting or putting that grain stats into the metadata, and we carry metadata, or they carry metadata to the decoder side, they decode the clean content, and then they use that grain module or the grain parameters. And then in the device size, the regraining happens. So this is an excellent idea. So this is a very cool idea that helps us to save a lot of bits. But the question is that, do we know what kind of denoiser, or whether our denoiser is good enough for this scenario or not? So do we know anything about grain parameters? What if we are estimating the grain parameters or the grain statistics in a wrong way? How about the regraining part? So imagine that we have two displays with the same grain parameters, but one display is applying the regraining in a different way or in a wrong way, and the other one does a decent job. And it produces some sort of a grain that is very much close to the source grain look and feel. How can we answer all of these questions? So we need a metric. So without having a metric that can assess the fidelity or similarity between film grain or film grain between the source and the test, we cannot answer these questions. We don't know whether our denoiser is good enough, or we don't know whether the grain parameter is good enough, or we don't know whether the regraining is doing a good job in the device size or a device side or not. So that's why we need the metric. But in essence, again, this is an elegant idea. You see the results of the SVT-AV1 encode with film grain metadata or with film grain synthesis capability. So still we have 10 megabit per second. We are spending 10 megabit per second on encoding that content by just following that SVT-AV1 framework. When they remove the grain from in the source side, and then they estimate the grain parameters, they pass it on in the form of metadata to the decoder, and decoder does the regraining. But still, there are a couple of issues with this SVT-AV1 stream. even though it looks better compared to that 10 megabits straight encode, like in HEVC or so, but still it's suffering from a couple of issues. The very first issue is that, well, the texture, the kind of the grain that we are seeing on the train is different than the native grain on the left-hand side. The other thing is that because of an issue in the regraining side, on the device side, actually, so we see a repetitive pattern. So again, I'm not sure if how well this video goes through the Google Meet link, but if you watch it specifically on TV or on bigger screen or so, you clearly see a kind of repetitive pattern, which makes it unrealistic. So people, they don't like this kind of, especially filmmakers, they don't like some AV1 streams like this with a repetitive pattern. So again, we need a metric. We need a metric to solve these issues, or at least have answers to a couple of those questions that they raised. A simple answer to a need for a metric is to, okay, we have a bunch of metrics. We have tons of metrics out there. We can use them and then just solve the problem. But the answer is that no, it's not that simple, because like all of these metrics that are out there, like SSI, MPS, and RVMAF, and another, and we have many other algorithms or full reference metrics. They're all pixel-based algorithms. So it means that like they care, or they measure the distance pixel-wise from, like in the same pixel, they look at the same location and they look for any deviation from that location and any distortion, and then penalizes the content. We can easily fail all of these frames, or all of these objective models, because for this kind of grain similarity use case. Because in grain similarity use case, a human visual system tends to perceive the texture or statistical signal like grain as a whole. They don't, the brain or the human visual system doesn't tend to look for the exact instantiation of the grain here on this frame and that frame, and then penalize any kind of distortion. But like whereas the objective models, they are actually pixel-wise, they operate pixel-wise. So any kind of deviation in pixel levels, it will be penalized heavily. So and again, we can easily fail all of these objective models or metrics. So look at this example. We have this one kind of image. I added Gaussian noise with the same standard deviation and mean. So the mean and the standard deviation are the same. Like it's a Gaussian noise, but like I added 2 times, one time to the left and one time to the right. And of course, the instantiation of those film grains are different, or noise are different, because it's a random noise. And then there is no guarantee that those grain happens in the same location. And you see that how low the objective metrics are, because again, they penalize any kind of deviation in pixel domain and pixel to pixel measurement. Then they perform pixel to pixel measurement. So here we design in IMAX, we design a metric that is solution to those problems. That like the IMAX Film Grain Similarity metric measures the fidelity and the similarity between the source and the test or encode only in case of based on the film grain. So it cares about the texture of film grain, and it assesses any deviation based on just, again, film grain. And it ranges from 0 to 100. So 0 to 20 means that like the film grains are very dissimilar, and 100 means that they're very identical or very similar to each other. And this demonstrates some of those examples, like you see how bad this film grain is, and the other one and the other one. This is a kind of in the fair range or so, but this one is very close to the source. How can we use this metric in one of the use cases that I just talked about it? So in use case number 1, when typical solution is to increase the bitrate values, we can, having this metric, we can adjust and we can find the optimum bitrate value scene by scene. So for each scene, we can run this film grain similarity metric, and then we can hope or we can target something above, let's say 81 or 80. And then we can decide on the bandwidth. So maybe if the 8 megabit per second is giving us 55, then we can easily increase it to something like 12 megabit per second and achieves like a 75 or 2590. So this solves one of those biggest issues that like in the previous scenario, when there was no metric or so, people, they had to watch scene by scene and increase the bitrate values, and then assess on a TV or maybe a big theater. So what bitrate values is enough for that specific scene. But here, when we do have a metric, then they can do it automatically. What happens in use case number 2? Like in the scenario of the film grain synthesis, so we can optimize every module down the chain. So we can look at the denoiser, how good the denoiser is. We can look at the grain estimation, look at all the parameters. We can even look at the regraining part. And then by just running this objective metric and measuring the distance in film grain, we can automatically optimize those components. This shows one of the examples. This slide shows one of the examples and one of the experiments that we did towards that goal. So we started with some sort of an analog film, and then we run IMAX DMR. So IMAX DMR is digital media remastering tool. So this does the degraining for us, or kind of denoising, if you wish to call it. So once the grain is removed, so the next job is to add the grain metadata into SVT-AV1. But this time we don't use the grain estimation from SVT-AV1. So we disable that grain estimation. We say that, well, here we wanted to fine-tune or find the best AFGS1 parameter. AFGS1 stands for that kind of a metadata for film grain SVT-AV1. So we find the best parameter. What is the success criteria? The success criteria is that if we put that kind of grain back and then we compute the IMAX FGS between the source and the decoded version of SVT-AV1, then the IMAX FGS is the maximum. So the success criteria, the success criteria for picking up the optimized film grain parameter is to have the maximized IMAX FGS metric. And then we did the same thing on the same kind of sequence, and we got pretty much very close look and feel of the grain. And here for this content, we are still in 10 megabit per second. There is no repetitive pattern. The grain is very close to the source, and the IMAX FGS score is kind of 95. You may ask about how we designed this metric, how we came up with this metric. This is a completely a data-driven approach. So we realized that modeling grain mathematically is very, very difficult. So then we said that with the advancement in the computer vision and the machine learning, why not using machine learning to do that, or data-driven approaches? So like human visual system that sees a lot of film grain and then somehow comprehend the overall statistics of the grain to decide whether that grain is similar to the source or not, we did kind of the same thing. We started with the saliency detection. We focused on mostly flat region, because this is the way that human visual system focuses on when it comes to the film grain assessment. And then we do like a feature extraction. We extract important features, and again, it's a data-driven approaches. The network by itself learns what are the important features for assessing the film grain similarity. We have a statistical measurement module. It's very important, as I told you. Human visual systems, it doesn't perceive like the grain as similar to like how the human visual system perceives structures or edges or contours. So this is different. We are dealing with texture, which is kind of a statistical signal. We are dealing with kind of film grain, which is again human visual system perceives the statistical properties of it as a whole. So we have a statistical measurement, and at the end we perform similarity measurement on those statistical features. And this is how we derive our IMAX FGS scores. Of course, like every data-driven approaches, we had to use a very important and very good training data sets. They're not very training data sets for this specific use case. We had to build our own training data sets. We did a lot of subjective study. We asked and we varied many and we over many iterations of film grain synthesis and addition and reduction or so. And then we asked experts on IMAX, mostly IMAX experts, to watch them and give us scores from 0 to 10 or 0 to 100 to the similarity of the grain. And we use those kind of data sets to train the metric. So I stop here, and I'm happy to answer any question if you have.
I was wondering, so would the metric capture the denoising aspect as well? So if you were to do the denoising and had whatever the clean plate, would the metric score it poorly?
Yes. Yeah.
Yeah. Okay. In that example where you had all the metrics and the different scores, you don't have an example where it was cleaned, do you?
Let's see. I think if there should be something like oh, you mean this one?
Yeah.
No, I don't have any clean. No, sorry.
Yeah.
This one with 79 is it's a little bit smooth. It's a little bit smoother than the original, but it's not actually clean. So there are some grain in it. But yes, we tried. We tested this metric. We had kind of a grainy content and clean content, and we see that it penalizes heavily. The other good thing about this metric is that it's not very sensitive to the compression artifacts. So in fact, that if we have a very we remove we remove a film grain, we do a very heavy compression on, let's say, SVT AV1 on the clean content on clean plate, and then we add the same or very optimal version of a grain back. When we run this algorithm, so it's just sensitive. It's sensitive only to film grain similarity. It doesn't care about the kind of blockiness that can be introduced because of the heavy compression.
And if there's a lack of film grain in the original, what does it score? And there's like a lack of.
Good question. Yeah. So we tried clean versus clean. So imagine that there is no film grain at all. So we have like a clean content, and then the output is clean after the compression, and we see that the score is actually 100. We didn't train, honestly, we didn't train this model and for this specific use case when the input is clean and the output is clean. But in our testing, we realized that, okay, the metric is giving us 100, which is good. So we say that, well, there is no grain distortion in this clean content. Or so if someone wants to combine this aspect, like a film grain similarity with the other part of the aspect or the other aspect of the quality or measuring the quality, like the encoded performance scores that we have in IMAX, they can easily do that because it's safe. If it's only sensitive to grain and it's for clean content, it's giving us 100, it will be easy to combine these two.
Any other questions? Okay.
Hojat, just one question.
Yeah.
You mentioned the first use case. Where do you see that applicable? Is that kind of in a production mezzanine type of environment?
Yes. Yeah.
Okay.
Yeah. So right now we do have some customers that they're not sure about how much to spend on some titles, and again, those titles are very grainy, and it makes sense. They still use like that one size fits all approach, and it's very difficult for them to pick another bitrate values for content that's grainy because it requires a lot of just visual validation and watching.
Yeah.
So yeah.
All right. Thanks.
Okay. Thank you, Hojat.
You're welcome.
So